Hi everyone, I'm Said Nalujifar. This is the presentation for our work, Is Private Learning Possible with Instance Encoding? I'll do the first half of the talk and then Florian will continue with the second half. The process of machine learning starts with a training set that is labeled according to some concept function C, and the goal of the learning algorithm is to look at this training set and find a good approximation of that concept function. So this process can leak some information about the training set used, and the study of privacy-preserving machine learning aims at finding private algorithms that can minimize such leakage. Instance encoding is one specific idea that could be used for achieving privacy-preserving machine learning, where we have an additional encoding step added to machine learning pipeline. So before applying the learning algorithm, we first encode the training set into this intermediate object that we expect to be private by achieving some notion of privacy. For example, we might want the encodings to be non-invertible, or we might require the encodings to have some stronger indistinguishability guarantees. But in both types of definitions, no matter how we define privacy, the learning algorithm here is expected to just learn by looking at the encodings. Why would this be nice? So such an encoding could be really useful to achieve two types of privacy at once that are both proven to be very challenging to achieve. So it can achieve private computation because these encodings are supposed to not reveal information about the inputs, and the computation could still be done on top of them. So this means in the multi-party learning scenarios that privacy is important, such as healthcare, the data set owners can just reveal or share the encodings of the data without worrying about extra privacy leakage. It can also provide private outcome like what we have in differential privacy. This is again because the algorithm is being applied on top of the encoded data. And no matter what the algorithm does and what the output of the algorithm is, the final output will be at least as private as the encodings. And everything will boil down to just analyzing the privacy of the encoding. So if we have such a private encoding, these two types of privacy will be obtained immediately. One instantiation of such instance encoding mechanism is Instahyde that was introduced in last year ICL. So Instahyde proposes a way for achieving privacy without sacrificing accuracy or efficiency, and they actually win a Bell Labs prize for their contribution. However, the privacy of their scheme is not well understood yet. So in this work, one of our goals was to first understand how private this Instahyde algorithm is, and we also wanted to have a more general treatment of this privacy to true instance encoding idea. So for first question, we provide an attack that breaks a challenge dataset that the Instahyde authors provide, and Florian will talk more about this challenge. But here I'm gonna give you a high-level idea of how our attack works. But before that, let me give you a summary of the Instahyde's encoding algorithm. So this algorithm has access to two datasets. One private dataset that is a labeled dataset and is a source of learning. And there is also a public dataset that is not labeled and we don't care about its privacy, and it's only there to help the encoding algorithm. So how is the encoding done? So first, the encoding algorithm samples a bunch of images from the public and private dataset and combines them linearly together to get this combination. And after that, there is this masking layer where each pixel in this image has its sign flipped with a randomly with probability half. So after that, we get this image that doesn't look like anything to human. But if you gather enough of them and feed that to a learning algorithm, it still is able to learn a good classifier out of these encodings, which is surprising on its own. Now, how do we attack these encodings? So we have this challenge dataset that is a bunch of encodings, and we are supposed to invert them to the original images that were used to produce them. So the first step of attack is the clustering step, where the goal is to match these encodings together based on which image they are encoding. So we train a neural network to do this clustering for us. And after that, we have this recovery step where we use the cluster information to come up with the image corresponding to each cluster. After these two steps, we can actually get a very good recovery of the images. I'm not going to elaborate more about the details of these steps, but I suggest you to have a look at the paper for that. But here is a sample of what our attack does. So the extracted images that you see here are very close to the original images that were used to encode the challenge dataset in the Instahyde challenge. So this shows that Instahyde is not as private as first thought, and we basically have a complete break of their challenge. Additional to our attack against Instahyde, we also have some theoretical results showing some barriers against achieving privacy through instance encoding. As we want to prove theorems here, we have to work with formal definitions of privacy for instance encoding, and Instahyde doesn't come with any formal definition, so we had to define our own. So we have this protocol with encoding, and we also have a fixed concept function. For example, you can think of the dog versus cat concept function. And we define a security game for this setting. So in our security game, the first step, the adversary selects two instances that are labeled the same according to the concept function. So for example, it should be either two dog photos or two cat photos. And then the challenger will encode one of these two images or instances and sends it to the adversary. And now the adversary has to decide which one of the images were used to come up with this encoding. So the advantage of the adversary here is the probability of guessing correctly which image was encoded. Note that here we are forcing the adversary to submit two images with the same label because we don't want the advantage to increase by leveraging the label information that exists in the encodings. Now that we have our privacy definition, we can ask this question. Can we achieve privacy and accuracy together using instance encoding? It's important that we want to achieve them together because achieving privacy alone is not a hard task. But there are two ways that we can define accuracy here. The first way is by defining accuracy on top of the encoded data. So in this setting, we have our first barrier that says that if a learning protocol with encoding can achieve accuracy half plus epsilon on for two different concept functions, then there is a polynomial time adversary that can break the security game for both of C1, C2 with advantage half plus omega of epsilon. So the key idea here is that if the algorithm is going to achieve high accuracy on the encoded data, this means that the encodings should have information about both C1 and C2 in them. So this means the adversary can actually use the information about one of the concepts to break the security game for the other one. So this idea only works if we define accuracy on encoded data. So we have another theorem about the case that you define accuracy on original data. So in this setting, we have a very similar theorem, but with the difference that our advantage here depends on the sample complexity. So the advantage of adversaries here is half plus 1 over n, where n is the number of examples in the training set. So this is slightly worse than the previous bound, but still sufficient to prove impossibility of achieving cryptographic levels of privacy for instance encoding together with accuracy. So that was the first part of the talk. I'll leave the rest to Florian.
For the second part of this talk, we'll look a bit more closely at the Instahyde challenge that was released by the authors. Releasing security challenges is not uncommon in machine learning security these days, and we'll now discuss some of the goals that we should strive for when designing security challenges and the role they should play in arguing security of a system. The main message I want you to take away here is that a security challenge should never be used as a substitute for a formal security claim. In fact, when we design a secure system, the very first thing we should do is to provide a falsifiable claim of the security goals that the system is meant to achieve within a formally defined threat model. And this is the single most important step if we want to treat security as a scientific discipline. After that, it's of course great if we can prove something about those security claims, but that isn't always feasible, and that's okay. Instead of a formal proof, or maybe in addition to one, we can also publish a challenge to invite the community to try and attack our system. And such a challenge should be designed to capture a necessary condition for the system's security, so that if someone solves the challenge, this implies that the system is insecure. The converse is not always true. Usually the failure to solve a challenge is not enough to convince us of a system's security. Let's look at a specific example that everyone's probably familiar with, Rsa encryption. Today, we have strong formal security claims for RSA. For example, that it is indistinguishable under chosen ciphertext attacks with proper padding. But note that this security claim cannot be directly captured by a static challenge because it involves multiple rounds of interaction between an adversary and victim. But static challenges are still very useful to measure and drive research progress. For example, 2 decades ago, RSA published a suite of factoring challenges, and these challenges satisfy our earlier stated goal in that solving them indeed would falsify RSA's formal security guarantees. But we don't know if the converse is true. It might be possible to break RSA in other ways than with factoring. While such challenges can be useful, it's also very well accepted within the crypto community that a static challenge is in itself not sufficient as a measure of security, even if the challenge is hard to solve. Because by that metric, the cipher used by the Zodiac killer could even be considered secure, since it took over 50 years to crack it. But it definitely isn't considered secure according to any modern notion of cryptographic security. So let's now talk about the Instahyde challenge, which was released to test the security of the Instahyde protocol. This challenge consists of 100 images that were each encoded 50 times using some undisclosed public dataset. And to solve the challenge, we have to reconstruct a close approximation of these 100 private images. And we use the attack that Saeed presented earlier to solve this challenge and recover all the private images. So according to the goal we stated earlier for a security challenge, this should mean that our attack invalidates Instahyde security claims, right? It turns out that no attack can actually do that because the Instahyde protocol does not come with any formal and falsifiable security claims. All we have is this challenge. And this is a major problem because in the absence of a formal security model, the only thing we're left with is the threat model that the challenge implicitly defines, namely that an attacker gets access to 50 encodings and has to recover the private images. But this threat model is a bit simplistic. And to make things worse, there are actually ways in which the challenge makes the attacker's job both easier and harder than in an actual deployment of Instahyde. For example, a real adversary would probably have some prior knowledge about the type of data that is being encoded and what public data set is being used. The adversary might also be able to actively participate in the protocol and aim for a slightly weaker goal than full reconstruction. The challenge doesn't allow for these things, and so in this sense, solving the challenge is harder than breaking the Instahyde protocol, which is fine. The bigger issue is that the challenge also makes some things too easy for the attacker, such as giving direct access to many encoded inputs computed over a small dataset. And our main attack on the challenge obviously exploits all of these capabilities. But this also means that whether the challenge gets solved or not cannot conclusively tell us anything about Instahyde security in a different threat model. For example, we also consider a slightly different threat model in our paper, where the adversary does have some auxiliary knowledge on the data that Instahyde protects, and in particular, we assume the adversary has access to the public data set. And under these assumptions, we give a very efficient attack that scales linearly with the size of the encoded data and can recover a private image given a single encoding. In many ways, this attack might be more realistic than the one we use to solve the challenge. But this attack fails to solve the challenge because it operates in a different threat model. So this brings us back to our main takeaway here that a challenge is really not a substitute for formal security claims in a well-defined threat model. Of course, this doesn't mean things would have been better if Instahyde hadn't come with a challenge. Publishing a well-designed challenge is always a good thing, but we always first need formal security definitions and security claims to base the challenge on. Taking a step back, I'll conclude the talk by noting that many of the issues that our work raised for instant encoding schemes are not uncommon in the broader space of machine learning security today, and that there are many systems that are being designed and proposed for various security properties of machine learning, but these properties are often not defined very formally, but rather expressed as informal desiderata about the costs of successful attacks. And in turn, the evaluations of these systems are also often incomplete and typically limited to testing that prior attacks failed. And I think that these problems are exactly what people in this audience are uniquely qualified to tackle. If you like attacks, that's good news for you because there's currently way more new systems being proposed here than can be rigorously evaluated. And if you like formal security and coming up with nice definitions and threat models, there is also a huge amount of cool work to be done in this area towards the goal of a much more rigorous and formally grounded approach to machine learning security. Thank you.